Okay, next up is Ben from Gensyn. Welcome to Korea. I know it's been a hard subway journey on the way, but you made it, which is great. 저희 벤 젠슨 님께서 이제 오셨는데, it's the first time in Seoul, right? 처음으로 서울 오셨고, 저희 이제 큰 스폰서이셔가지고 이제 참여하게 되셨습니다. 일단은 the talk of your title is Future of Machine Learning is Decentralized, and you have your slides with you. So 일단 박수 부탁드리고요. 큰 박수 부탁드리겠습니다. Big round of applause for Ben.
Thanks so much.
Oh, you can use this one. Sorry.
Thanks.
Speak into it. Yeah.
Hey everyone, I'm Ben, co-founder and CEO of Gensyn. As it says up here, the title of my talk is The Future of Machine Learning is Decentralized, but this is a condensed version of a much longer talk, so I'm going to try and kind of make it fit into the time that we have, but please excuse bits that I kind of go through quickly or bits that I don't go through at all. If you want to find out more information, there's tons of information online about what we do and kind of the history that I would otherwise go through in this talk, but probably won't have time to today. So for the talk, I'm just going to go through a brief history and progression of machine learning. So this explains a little bit about why I think the future of machine learning is more and more decentralized as we go, and the trends that we've seen already purely in the AI machine learning world, nothing to do with crypto or blockchain, and then go on to why it's related and why it benefits from crypto and blockchain technologies, etc. Present some opportunities, some of the challenges that stop these things from happening, and then finally some solutions, and obviously including what Gensyn does, why we care about this, how we're solving those problems. So very quickly on me, so I'm Ben. My background's in machine learning research originally. So I did my PhD in deep learning focused on neural architecture search 10 years ago now, back when machine learning was still mostly within academia. I was working in computer vision, and I was focusing on using convolutional neural networks to do computer vision tasks. So detect objects in images, classify images, say if there's a cat in the image, etc. While I was doing that, I realized that a large portion of the work being done within academia on machine learning was focused on handcrafting neural network architectures. So taking the layers that you see in a neural network. So if you think of a transformer like GPT or BERT or any of the other kind of transformer models, they have a sequence of layers within those networks. And a lot of the research back 10 years ago was focusing on just finding different sequences of layers. And it was humans doing this. And I looked at that and said, why are humans doing that? They don't need to do that. We can automate that process. We can search for the optimal sequence of layers. And so I focused my entire research on that. And what I learned while doing that was just how expensive machine learning is in terms of resources. So training a machine learning model is very expensive. You need lots of GPUs typically. You need lots of data. You need lots of humans to label the images or the data set before you can train the model. And all of those upfront things cost something. They cost something in the real world. And for me, the bottleneck was access to compute. I just couldn't access GPUs. I had 4 of them under my desk. Google were doing the same research with thousands of them in data centers, but I couldn't do it. The techniques they were using were pretty simple. They weren't they're very complicated. I could understand them. I could propose new ones, but I couldn't run them because I didn't have 1,000 GPUs in a cluster. I had a small box under my desk as a PhD student with very little funding. And so I realized I was being held back from proposing novel research for humanity. And I didn't like that because that meant that many other people were being held back in the same way. So that was a huge learning for me. There's more information up there. I previously co-founded a data privacy startup as well. I feel very strongly about individual consumer privacy and how when we interact with businesses, we give up enormous amounts of data, which is very valuable. The current paradigm is that we just give that up in order to access the services, but there are other things that we could do. And blockchain feeds into that heavily. It didn't in my previous startup, but a lot of learning since then. It's just something to know. Moving on, 5 years ago, I co-founded Gensyn with that belief from my PhD that the resources underneath machine learning were constraining machine learning itself. It was moving slower. It was getting adopted more slowly in the world because of those constraints. And there must be a way that we can alleviate those constraints and get more people able to do AI and machine learning. So we co-founded Gensyn, myself and my co-founder Harry, 5 years ago in London. He'd experienced that compute problem as well, but from industry. So he'd been working in a startup where they were trying to solve insurance risk problems. They had data, they had the ability to build the models, but they couldn't get the compute, even though they had money. So he had a different problem to me where I just didn't have the funds as a PhD student to get the GPUs. He had the funds. The startup was funded, but they still couldn't buy the GPUs because there was a shortage. So it showed that this was even deeper than just money. It was deeper access issues existed around these computational resources, but also the other resources. Now, Gensyn's been going for 5 years. We raised our Series A just over 2 years ago now from A16Z. We've raised just over $50 million to date, and we have a team of more than 30 people distributed around the world focused on solving this. The majority of our team is very, very technical, mostly researchers and engineers building the solutions to these problems. So, moving on to the progression of machine learning and a little bit of history. So, as you can see up here, there are multiple categories that I've skipped through, so I'm not going to give you a very long history of machine learning. If you're interested, it's written up in various places, or I can send a much larger slide deck to you, which has a lot more information in it. But I've skipped through to 2021, rather than starting back in the 1940s, which this timeline actually does, which takes a very long time. So I'm assuming that everyone's aware and understands that machine learning in the early 2020s became kind of productized, basically. It moved out into the world where people could start using it, principally with ChatGPT, when we all got access to models and could actually run these models without being a researcher in a lab, running it themselves or figuring out how to host it and then accessing it. So before then, a lot of it was kind of within academia or within industrial research labs. Post the early 2020s, it came out and more people were using it. At that point, a load of scalability issues started happening. And what I think about the most is that machine learning moved from being purely research to being predominantly, when productionized, an engineering problem. So instead of figuring out what's the optimal structure of a neural network and how do we train this thing, it became how do we make the most effective model we can and how do we scale it over the infrastructure that we have to make it train effectively. And actually that stops being a research problem to a large degree and becomes just systems engineering and distributed systems. And so you can see that in the progression of the research up here where we got these distributed architectures. Pathways from Jeff Dean at Google showed ways of constructing neural networks on the fly. Rather than having one singular huge network, you could have many different pieces of network that are routed through as we handle requests. That led to things like DePaco from Google Research as well. There's Diloco, which does communication efficiency. We've got the Palm model from Google works with pathways underneath. It is inherently a mixture of experts model, which is this idea that you have many different small models within a model, and you choose where to route requests through that model at the request time. So instead of having this singular massive model sat in a massive data center somewhere, you can actually split that model over many different devices. That's really interesting from a purely machine learning perspective, but it's particularly interesting if you scale it out even further and say this doesn't need to be in a single data center anymore. It can be in many data centers. It maybe doesn't even need to be in data centers. It could be on any device in the world if we scale it further and further and further. And so that's what Gensyn thinks with regards to machine learning. We think that the future of machine learning is massively scaled to the point where it runs on every single device in the world, effectively. But in order to get there, we have to solve some challenges, which I'll go into. There's more references up there. Please look them up. I don't have too much time to go into them right now, but a lot of things happened in that time period. Moving on into the future, so what are we looking at as we go from 2025 and beyond? I think we're looking at these much larger models, these federated models that exist over any device in the world. And instead of having a named model that you interact with right now, where you use Claude 3.7 or you use GPT 4.0 or something like that, actually what we're going to have is these continually living models that exist over the entire compute infrastructure. And so you might have a local model on your device, which is effective for your use cases. It's personalized for you on your MacBook, on your phone. That model constantly learns and constantly gets better at understanding you. When you make a request, it could go into that model, and then from that model, it could go to other models out in the world. And this starts to look a little bit like the internet as it stands right now. When you make a request on the internet, you bounce through many different servers looking for the one that handles your request. And when you get there, you pull the information back. But that's a very raw data style. It's this idea that accessing information on the internet is accessing some text in a database somewhere or an image in a database somewhere. That's the thing that you're requesting. In the machine learning world, you're not requesting that raw data anymore. You're requesting knowledge or insights. And those knowledge and insights could come from any model. If you think of a model not as this intelligent system that you talk to, but actually just a representation of data, which is more easy to interact with, then it changes the way we can think about the infrastructure of the internet itself, but also the infrastructure of machine learning. And the two merge into this highly federated infrastructure that requires a new set of protocols underneath to actually function effectively, which is what we at Gensyn build. There's more I could go into here around how we've moved from this kind of pure training and inference pipeline of machine learning to pre-training and then post-training and reasoning and reinforcement learning from human feedback, supervised fine-tuning, then inference, and those things are blurring more and more. Our view is that models in the future and very, very soon will just constantly train. They'll constantly train and they'll constantly run inference. And so when you're getting information from a model, you're just reading information from the parameter space that exists within that model. That could be images, it could be text, it could be anything that's been compressed into a shared parameter space. The example I always give is right now on the internet, if you wanted to store a representation of this room, one of us would have to take a picture or a video, or we'd have to describe it in natural language, and we'd store that in a database. In the machine learning world, we don't need to do that. We can cover this room in sensors, and we can generate a representation that's compressed into a new space. That representation can then generate its own images, audio, video, text. Any of these modalities are available from that condensed representation. So actually, you can think of machine learning as just providing this generalized automated compression mechanism that can be done anywhere and doesn't require human input. If you think about it in that way, scaling the effectiveness of machine learning across the world isn't bottlenecked by humans anymore. It's bottlenecked by electricity to run the models, to execute the computations, and it's bottlenecked by data. And also human labeling and kind of knowledge. We have to give the machines the way of actually understanding the data. But if we solve those three things, we can actually scale this with electricity, which is much faster than scaling it with humans, which is the current way we do things. Again, more to go into on inference time compute, these reinforcement learning processes, etc. Please do take a picture, read up on these techniques if you're interested. Obviously, contact me as well if you want to talk more. Moving on, I probably don't need to spend much time on this. I originally gave this talk to a lot of machine learning people who didn't know very much about the world of decentralization and blockchain. I've covered a brief history here, going through the starting in the financial world with Bitcoin, moving into computational, where Ethereum showed that we could do generic computations at the consensus of a group, i.e. we don't need a human participant to verify something anymore. We can do a computation and know that it's done correctly using the Ethereum blockchain. Moving on from that, we got a lot of infrastructure. So using those principles, using this idea that we could verify small arbitrary computations, we realized we could use that to coordinate resources. So things like Helium coordinating network infrastructure, things like Filecoin coordinating storage. These same things can happen theoretically for any resource. And so we at Gensyn think about how do we expand these principles to the resources under machine learning? How do we build that specifically to unlock machine learning scalability? Finally, we've got some very interesting coordination techniques, DAOs, retro public goods funding, the idea of crowdsourcing funding for something, creating a fair market over a resource rather than having a constrained market as we currently do with the cloud providers, etc. Many, many downstream things become available. So moving on to opportunities. The opportunities of machine learning, I probably don't need to spend too much time on this. I don't know how big believers people are in machine learning, but in my view, it is the next step change for humanity. It's taking us to a completely new world. It's equivalent to when we discovered electricity, if not larger. It essentially changes the world of digital knowledge away from being human curated and limited by humans to being machine curated. We can create, theoretically, a digital twin of absolutely everything in the physical world that is constantly up to date at all times, generated and run on all of our devices at all points of time, that you could query and you could pull out any modality of data. So you could interact with this representation of the physical world at all times just from a device in your pocket. You could pull out new images, new video, new audio, new text, any modality on demand. It could answer any question on demand. Right now, we get a glimpse of that with chat systems, but those chat systems are manually created by people. They're stuck at a certain point in time, and they don't have access to all of the data, all of the sensor data that exists in the world, because the way we build build those models right now is limited by humans. There has to be a human reviewing things. There has to be a human verifying that things have happened. There has to be humans signing contracts to access resources, etc. We can remove all of those human links with technology, meaning we can scale this essentially infinitely over the resources that we have in the world. Another discussion, this is more of the limitations, more of the physical limitations of machine learning right now. So electricity, the biggest one, it's the core resource of machine learning. We think about GPUs, NVIDIA H100s, B100s, etc. They are the refinement tool for electricity. Underneath it all, electricity is the resource that needs to be harnessed for machine learning. We can make many different ways of refining it into machine learning operations. We could have custom ASICs, we could have new GPUs, we can have CPUs. There could be an entirely new architecture of processor which does this processing. At the end of the day, electricity is what matters. It does mean, though, if you're to build a protocol or you're to build technology which allows machine learning to run on any device in the world, you have to be able to deal with completely new devices. You can't just build technology that runs on an NVIDIA GPU or that runs in a trusted execution environment. You have to be able to support all of these new devices, including the ones that haven't even been built yet. Other limitations, all in the centralized world. Can we build bigger data centers? Can we cool those data centers? Can we find people to work in those data centers? Can we create fast enough interconnects between those data centers? All of these are bottlenecks on the centralized machine learning world that would not exist on the decentralized machine learning world. Lots of challenges to this. We've heard a lot about these in the media many times. Safety, ethics, bias, the idea that power accrues to the creator of these models. We think all of these things are solved by decentralization. The true problem with machine learning and the true danger of it is if we let it get into the hands of a small group of people and out of the hands of everybody else. We think that everybody has the right to build machine learning technology, not just use it, and we should all be able to do that. That solves the bias problem. It solves the problem that when you use ChatGPT right now, you're using a model curated by a small group in San Francisco, not a model that's been created by many people around the world. Well, the solution to that, in our view, is many models around the world. You should be able to pick which model you use at any point in time, and there should be millions, billions of models all coexisting and able to be used. If you can't find a model that reflects the biases that you personally have, then you should be able to create a new model with those biases and offer it out to the world. At the end of the day, our view is that machine learning should reflect human biases, i.e. every person in the world is differently biased, and that's what makes the interesting diversity in the world. Bias isn't a dirty word, it's a good thing. Every machine learning model is a biased machine, so let's allow infinite models to exist and reflect infinite biases that exist in the world, rather than trying to create this single model that's meant to represent everybody's opinions in humanity, and in the end ends up satisfying no one. There's a race right now to capture the ability to build those models. It happens at the resource layer, it happens in capturing GPUs, it happens in capturing electricity, and it happens in capturing regulations. The large tech companies are trying to capture the regulations and stop other people from building models right now, and that shouldn't be the case. We can solve that with technology rather than regulatory fights, and that's what we'd like to do. Running low on time, so I'll skip through this quickly. This is what we do at Gensyn. So we build four main things, or we focus on four main problem areas. The first is execution. So can we consistently execute machine learning operations on any device in the world? That is, if you do part of a machine learning model execution on your phone, another part on your laptop, another part in a data center somewhere, are all of those things compatible? Are they comparable with each other? Right now, no. There's many different software stacks. NVIDIA has CUDA, which is a huge moat for them. No other companies have a version, a software package, anything like CUDA, which means that NVIDIA has a stranglehold on the market. That doesn't need to be the case. There can be a new compiler stack which exists and allows for execution across heterogeneous devices and compatibility between those devices. So you could theoretically split a machine learning model between your phone, your laptop, and an NVIDIA GPU without having to think about different layers of the software stack. That's just handled for you. It just hasn't been built yet. We're focusing on building that. The next one is communication. So can those devices talk to each other in a standardized way? Can your phone talk to your laptop? Can your laptop talk to a data center? Can it talk to a GPU on your desk? Can it talk over a local network and over the internet in the same way? Right now, no, not really. It can't communicate tensors, matrices, the low-level data types of machine learning in a standardized way between these devices. But we build that technology as well. So peer-to-peer communication frameworks to allow any device over any network to talk to any other device in a standardized way about machine learning operations. Next up, verification. Can the devices trust each other? Theoretically, with the first two, we have the ability to execute machine learning operations consistently over every device in the world. We have the technology to let those devices talk to each other and share matrices, tensors, parts of models, parts of neural networks, execute across these devices whenever we want, but those devices can't trust each other. They don't know who's running the other device or what their motives are. Right now, we solve this with legal contracts between humans. That doesn't need to be the case. We can solve this programmatically. So low-level libraries to allow a single device to trust the execution of another device when it outsources computation to it. And that can happen through cryptographic proofs, probabilistic proofs, game theoretic proofs, etc., all secured by a chain and the consensus of a chain underneath. Finally, coordination. How do we actually use this resource? If we can trust all the devices in the world, we can execute across them, we can communicate between them, what do we use that for? How do we run machine learning across those devices? And so finally, you have coordination to create new models that exist over this infrastructure. That could be a mixture of experts models, where everyone is running an individual model and we're routing through them, or it could be one huge model that's sharded across every device. Either way, those training runs and those inference runs need to be coordinated somehow, and we build the technology to do that as well. So here's a list of the technology we've released so far. We have our own compiler, or we've built so far, some of it's unreleased. We have our own compiler, we have reproducible execution libraries, we have execution frameworks for execution. We have something called RL Swarm for communication. We have HDE, skip pipe, efficient communication methods for growing neural networks or training neural networks over large numbers of devices. We have Verde, which is a verification system for trusting outsourced execution on different devices. We have our testnet, which is an Ethereum rollup which coordinates RL Swarm training runs across any device in the world. I'll go on to explain a little bit more about that, although I am out of time, so I'll be very quick. Final couple of slides. We're in testnet now. We've released RL Swarm as our first testnet application, but underneath everything, our testnet is designed to get out those 4 pieces of technology I described. So we get out our compiler for execution, we get out our communication libraries, we get out our verification libraries, and we get out the coordination via the chain. RL Swarm is something you can run today. So on a MacBook, on a GPU, you can download the software. It's open source. It's on GitHub. You can run the software, and you can join the testnet. In doing that, you are locally training a machine learning model, a minimum 500 million parameters. You can run whatever size you want. I've run a 1.5B recently. You could run theoretically any size if you have access to the hardware to do it. When you do that, you join a swarm of models that train together. Those models communicate with each other over a standard framework in a peer-to-peer network, and they give each other information on how they're executing. They do reinforcement learning post-training, which is what DeepSeek R1 famously did recently. We do the same thing, but we expand it to a global case. So the model, rather than just checking their own thinking and reasoning, they reason together. They can talk to each other about their answers, and they can critique each other. In doing that, they improve together as a huge swarm of models. You can create many different swarms. You could create swarms from different data sets. This is all kind of open space. And because it's entirely open source, we're handing this out to the community and saying, please build on top of this. Please build new swarms, build new data sets, build new coordination mechanisms. We're fully EVM compatible. You can build everything within the EVM on the coordination side. The RL Swarm code base is fully open source. You can hack around with it. You can essentially do whatever you want with this. There's a list of things that you can do there. Everything is coordinated by our Discord, which I'd welcome everybody here to join. Finally, some stats on the testnet so far. So we launched it 11 days ago. We've had more than 12,000 participants so far who've signed up. We've trained more than 7,000 individual models on devices around the world. So those models are fine-tuned based on interactions between each other without a single centralizing party doing the training. They're all learning together. If they're different models, if they have diversity in the swarm, that benefits the swarm. We don't even know the models people are running. That's the whole point. It's fully decentralized. Finally, we allow people, or we put in the functionality for people to upload their models to Hugging Face. So when they fine-tuned, when they've done some more steps, they can put their model live for everybody else to use. And we've had more than 1,200 models uploaded to Hugging Face in the past 11 days by people running RL Swarm. More links there if you'd like to join, follow along, view the dashboard, etc. And that's it. I ran a little bit over time, so apologies for that. But if I have time for questions, more than happy to take them. Oh, I was watching that.
Thanks for the presentation, and I want to ask about the reason why you chose the Ethereum layer 2 as the coordination layer. So there are other projects that chose like L1s as the option. So
Great question. We actually originally were a layer 1. So for years we've been building this as a independent layer 1. But what we realized is over the past 4 years, the vast majority of the technology we built wasn't blockchain related. It was all the off-chain stuff that we need to do with the machine learning frameworks. And so we realized the vast majority of it, even when it came down to verification, which is the biggest reason we need a chain, is to terminate disputes somewhere at some consensus. Even when it came down to that, actually, all the work we did to make it more efficient and more effective was just off-chain work. And in the end, we could roll up all of the coordination, all of the verification disputes to the EVM rather than having to sit somewhere else. Our original intuition was we would need more configurability on the chain. We'd need the ability to change the way the chain runtime actually executed. What we realized is that's a nice to have, but it doesn't really benefit enough to justify creating an entirely new ecosystem. I think a lot of layer 1s, we're in a weird kind of time right now, but there are a lot of layer 1s are built as layer 1s because there's kind of funding reasons why it looks good to be a layer 1, but actually usability-wise, it's much worse for most people because you have to learn an entirely new stack, you have to learn to use new tools, you have to build new tools. It isn't really necessary outside of a very small number of use cases, and what we realized was we're not necessarily one of those use cases. In the future, we're open to it. Maybe we find a reason why we do need to branch out. But right now and for the foreseeable future, we can do everything we need against the EVM because we just did more off-chain work and realized that we can build our own off-chain libraries to mitigate the need for an entirely new layer 1. And that means we get to come to people and say, hey, if you want to write Solidity contracts, you can. You don't have to learn some entirely new smart contract framework to interact with Gensyn. You want to use MetaMask, you can. You want to use the normal exchanges, you can, etc. It just makes it much easier for the average developer to get involved, rather than us having a layer 1 for kind of hype or marketing reasons, rather than actual real technical reasons.
thank you.
Awesome. All right. Big round of applause for Ben. Thank you so much.
Thank you.